Hello, everyone. I'm Prof. Ogoke. I'm currently assistant professor of mechanical engineering at Carnegie Mellon University. And we started the Forge Lab, where I study AI for manufacturing generally this past fall. And I'll talk to you today about physics-guided AI for simulation-driven design and additive manufacturing. And kind of the motivation for this talk today is the fact that, as we've advanced in our design capabilities, we're also placing increased demands on the type of structure we have to create to meet these designs. So for instance, looking at this engine bracket, this bracket it's well optimized to maximize stiffness and minimize compliance. You can see a lot of very complicated structures have to be built here. There's a lot of structures, organic contours, and it's not always obvious, well, how do you build these structures in practice? And I think one natural solution is just additive manufacturing, where again, we're doing this freeform construction of a complicated geometry. So this might look like adding material to a substrate iteratively. And here we can see that we're able to create this complicated fuel nozzle by using additive manufacturing. But while this is pretty useful, it's not by no means a magic bullet, and you still have to be really cognizant of defects and physical constraints of additive manufacturing. So for instance, if you aren't mindful of that, you can have defects where, for instance, your support fails because your part laminates in the build plate entirely, have this massive crack in your part, or you have your part crashing into your machine and causing defects, or even more catastrophically, your part's completely destroyed during printing because it's distorted so badly it crashes the machine during printing as well too. And all these effects at the macro scale are driven by the thermomechanical effects during printing, which we try to minimize in some ways through applying design for manufacturing heuristics and so forth. But even if you do apply these heuristics, it's not guaranteed to be a complete that defect-free part. That's in part because of the fact that you have so much variability in your process of additive manufacturing a lot of the times. I'm going to use laser powder fusion as a case study here, where effectively we're melting powder with a heat input. And if I zoom in on where the laser interacts with the powder at a very small scale, it's an incredibly complicated physics simulation process where we have fluid flow, we have vaporization, evaporation, we have gases being trapped and causing porosity in our part. This is very, very complicated physical model I have to kind of deal with in this case, right? And this is really important because we can't ignore it because it influences things like defect formation. Again, we have these holes in our part if it's not correctly modeled. We can have different microstructures depending on how it cools down, as well as warping again, depending on how we're scanning our part during the printing process. So it's really important to be able to effectively model this accurately, but it's also challenging because this is at such a small length of time scale. It's micron scale length and microsecond scale and time. It's really hard to model this and have a good idea what's happening here just from first principles. So again, I have this complexity leading to defect and variability. So a lot of what I've been working on over the past part of my career, my PhD, and also my postdoc is trying to figure out, well, how do we reliably manufacture a part so we're not getting defects when we actually print the part in practice, so we can actually use this for good performance. So when thinking about this, kind of the typical approaches to doing manufacturability analysis is to do some experiments where you run a ton of experiments on your part. You kind of characterize it and you monitor what's happening during your printing process. But again, it takes a ton of material and time to do this process for completely characterize the entire design space. Or you can run simulations, which again are very expensive to do, have accurate models of behavior. So what I'm interested in looking at is, well, how can we use deep learning to reduce the amount of experience required, characterize performance, as well as making these simulations a little bit cheaper so we have less resources required for simulation modeling and practice, so we can kind of address, well, how manufacturability is my design and not have that take a ton of resources to do in the first place. And as a case study, I'm going to go into a little more detail about how this works at the melt-pool level scale and how we can bridge fidelities there. So for modeling any given melt pool, which again is where the laser hits the powder bed, we have a couple of different choices of how much detail we want to include in our model. We can go to one extreme, which is only analytical models, where we only consider conduction only and neglect a ton of other stuff. Or we can have a very, very detailed model where we consider all the physics happening at the same time, the fluid flow, velocity flow, temperature gradients, all of that stuff. But that, again, inflates our runtime from about 5 minutes for the simple model to 5 hours or days, depending on our scale, for this very complicated model. So I'm really interested in figuring out ways we could kind of bridge fidelities and maintain that accuracy, but not sacrificing speed in that case. And as a case study, I looked at how we can kind of bridge fidelities across mesh resolutions. So looking at from going from a very coarse simulation in software called Flow3D to model the overall melt pool to a very, very detailed simulation, which takes, again, more time, but it gives you more detail. and figuring out ways that we can kind of get this increase in resolution for free, where we normally have to pay for this computational expense as we go from 20 microns to 5 microns. Can we effectively go sideways in this process and get that same information from a hypothetical simulation, but without having to spend as much time running this entire process, right? So my thinking about this giving us the ability to do things like rapid sweeps over different designs and parameter spaces much more quickly, and also extending things to other geometries and parts much more easily as well too. And if you wanted to just do this process of going from a low fidelity to high fidelity simulation, I think one natural instinct is to take off-the-shelf model and just train a model to do that directly, like a CNN or any kind of physics-based model. But I think that at the core, this problem is technically ill-posed, right? You don't know exactly what the high fidelity solution is just from low fidelity information. You're losing type of information going from high fidelity to low fidelity, as many possible high fidelity simulations possible for one low fidelity input. So looking at this in a simplified two-dimensional case, looking at y as our target high fidelity case and x naught as our input, you have this probability space you have to kind of reason about of how the actual right answer lies in this probability space. So instead of trying to train a predictive model and is training to minimize like a mean squared error and just go straight to the right solution per se, it's going to give you a very blurry, very averaged over output over all the possible solutions. Instead, also actually sample from this distribution instead. So we're sampling different realistic examples of this multiple structure as opposed to doing it purely deterministically. So in practice, we actually do this in kind of integrating both paths together. So we have this first path, which is deterministic inference. We're training just kind of a deterministic model, a predictive model to go from low fidelity to high fidelity. And it's going to give us some kind of approximate high fidelity prediction. So we can get kind of large scale structures on average of how the melt pool looks high fidelity from this low fidelity input. Again, it's deterministically, there's no generation happening here. But then we can take that intermediate, that kind of approximation of high fidelity case, and we can use generative models to add in a small scale detail. So we're losing detail by going from low fidelity to high fidelity. Trying to sample it back and try to augment that intermediate case, that detail again, so we have some information about, well, here's my best guess as to what this small scale data might look like from this high fidelity simulation if I were to run this. And some of the takeaways here is that it gives us the ability to do things like first have a much more detailed estimate of the melt pool structure at any given point in time. So I have this nicely modeled contour as opposed to this very, very blurry case in other models. And more importantly, we also capture the variability in how this fast-changing areas of our melt pool evolve over time. So remember I said earlier, in microseconds and timescales, it's really hard to what's happening exactly, but we really care about how much that's varying, if it's unstable or stable. And we can have information right here with confidence bounds over our melt pool structure. And in cases where we have a very good idea what's happening and it's not varying too quickly, we also have a very small confidence bounds and a very accurate prediction here as well too, so that we can have this kind of variability models with this diffusion process augmenting our deterministic approach here. So now that we have some useful way of being able to do this upscaling from low fidelity to high fidelity at the melt pool scale, these are further extensions that could be interesting to explore further. Following some more work from my postdoc is to look at ways we can model these defects or the part scale as opposed to the very, very small melt pool scale. So again, looking at how this will apply to evolving temperature and displacement over the entire part of the macro scale. And also, following up on some of the points brought up earlier today about how we can bring this into real worlds, figuring out how we can help experimentalists by pre-training simulation data and kind of closing the gap between experimental-based data, solution-based data. So if you're out in the fields trying to optimize your printing process with real data, you don't have to spend as much time running parts over and over again to get a good estimate of what's happening in your printing process. And in the big picture, as I grow my lab from the first semester going forward, I'm interested in these three big concepts and applying AI to manufacturing. So first one being forecasting of, well, how do we reliably predict this multi-scale behavior that shows up a lot in different processes, not just in this one I showed today, but in a lot of different other processes as well too. How do we model variability for behavior that's hard to model or observe a priori with generative deep learning, as well as, well, how do we efficiently leverage large data sets and again, try to bring some of those foundation model concepts into the world of experimental manufacturing so we can have these insights without as much manual labor. So with that, I will take any questions at this point, and thank you for listening.
Maybe we can have 2 questions from the audience. Okay, thank you for the nice talk. So I have two questions. First question regarding the defects. So one basic question. So does the defects always bad to the parts?
Yeah, that's a great question. So defects are usually undesired when we don't know they're there, because if we're trying to print apart some desired performance, and let's say there's a hole in my part somewhere I didn't know before I designed it or before I printed it, that's going to throw off all the performance data that I thought we were going to have and have it be completely different in practice. So it's going to shift away from the design requirement to some other experimental actual performance.
Right, thank you. Yeah, the reason why I'm asking this question, because sometimes let's phrase it another word. So sometimes we call it imperfections, right? So when during the printing. Actually, some experiment surprisingly has experiment results shows that some type of imperfection can actually further enhance the mechanical properties of the parts. So I do a little bit of wrap, right? So for the structure design. Yeah, so the second question following this, right? So because this type of defect or imperfection always because of the process uncertainties, right? So high temperature, the voltage, this type of process dynamics lead to this defects. So how do your AI model or machine learning model incorporate this kind of dynamics, or characterizing this kind of uncertainties? And also then how do you incorporate this to predict the uncertainties, or what's the following rectifying strategy?
Yeah, that's a really good point. So also, a lot of this builds on the idea of eventually being able to control these processes by having these fast circuit models. And part of the reason why I chose to do this upscaling process opposed to going directly from, let's say, a voltage or a power or velocity or some process parameter directly to the end result is the fact that what you normally prescribe as the process parameters doesn't always match what you actually see in practice. So things like the geometry effects can confound those variables. So if you're near some kind of corner or have heat buildup in some places, that means that what might be a good parameter to use for the entire part might be cause defects in other areas of the part as well too. So this kind of gives you a way of kind of looking at the small scale behavior in that low fidelity space and upscaling it that way and kind of understanding how that might influence defect formation at the high fidelity case in that sense. Yeah.
Great. Thanks, Francis.
Thank you so much.
You can wrap up. Thank you.